Dear students, today we are going to discuss about conductors in electrostatics. First of all, first point is what in electrostatic equilibrium means what? When charge is not moving, when charge is in rest state, then electric field is always zero inside the conductor. Conductor in the electric field always zero. For example, see, here is a uniform electric field I have taken. In that uniform electric field, one conductor means what? Metal block I kept. And here also uniform electric field, but I kept dielectric means what? Insulator. Metal block consists of free electrons, crores of free electrons. Then what happens as soon as it is kept inside the electric field, electrons will displace towards left side oppositely to electric field. इलेक्ट्रिक फील्ड को ऑपोजिटली डिस्प्लेस होकर ये सरफेस पर जमा हो जाएंगे इलेक्ट्रॉन्स. ये दूसरा सरफेस पर ऑटोमेटिकली शॉर्टेज ऑफ इलेक्ट्रॉन्स, दैट मीन्स पॉजिटिव चार्ज. इस तरह चार्जेस इंड्यूस हो जाएंगे. दिस इज कॉल्ड इंडक्शन. इंड्यूस हो जाने से इसमें क्या होता है? दो फील्ड्स, अप्लाइड फील्ड ई विच इज लेफ्ट टू राइट एंड इंड्यूस्ड चार्जेस के कारण फील्ड ई आई विच इज राइट टू लेफ्ट. बोथ विल बी एग्जैक्टली इक्वल इन केस ऑफ कंडक्टर. That is why net field will become zero. So inside the conductor, electric field will not be present, even though it is placed in external electric field. वो external electric field में रखने पर भी अंदर electric field zero ही रहता. लेकिन dielectric medium में क्या होता? It consists of dipoles. The dipoles will come in field direction in chain shape like this, due to which some dipoles tails means what? Negative charge is on the first surface. Some dipoles heads, which is positive charges, are on the right surface. Because this is called polarization. Polarization से जो charges induce है ना, उसके कारण field EP opposite, applied field is left to right, polarized charge के field right to left, but both will not be equal here. Applied field is always greater than field due to polarization. So that is why net field will not become zero inside the dielectric medium. Net field En is equal to E minus EP. That will be equal to E by K, means what? 1 by K of E. So field will simply reduces to 1 by K, but not becomes zero in case of dielectric medium. Second point is electric field just outside the conductor is always perpendicular. Electric field just outside the conductor is perpendicular. For example, this is a charged body, metal charged. On the surface, charge will be present. Suppose imagine electric field is making some angle theta with the surface. Then what we can do, that electric field we can split into two components. E sin theta perpendicular to surface, E cos theta parallel to surface. ये parallel to surface जो component है ना E cos theta, उसके कारण क्या होना पड़ेगा? ये surface charge पर force ऐड किया जाता. इलेक्ट्रिक फील्ड से चार्ज पर फोर्स ऐड किया जाता ना, E की फार्मूला के हिसाब से. So force के कारण this charges should be in motion. Means what? Equilibrium will not be present. Means what? Static condition में नहीं रहेगा. Electron charge should be in motion state. But the conductor charge देने के बाद within fraction of seconds equilibrium में आ जाएगा. Charge will remain in rest. So that is why E cos theta should be equal to zero. ये फील्ड नहीं रहना पड़ेगा. पैरेलल फील्ड, सरफेस को पैरेलल में रहने वाला फील्ड जीरो होना पड़ेगा, क्योंकि वो फील्ड के कारण चार्जेस मोशन में रहना पड़ेगा. लेकिन हम लोग इक्विलिब्रियम में आया हुआ चार्जर बॉडी को देख रहे हैं. एक बार चार्ज देने के बाद बॉडी विथिन 10⁻⁸ सेकेंड्स इक्विलिब्रियम में आ जाएगा, रेस्ट में आ जाएगा, मोशन में नहीं रह पाएगा. लेकिन ये फील्ड अगर पैरेलल रहा तो पैरेलल सरफेस के पैरेलल में कोई कंपोनेंट ऑफ द फील्ड रहा तो उसके कारण चार्जेस मोशन में रहना पड़ेगा, बट चार्ज रेस्ट में है. So that is why this field should not be present. That means what? It should become zero. That's why cos theta should be zero. That's why theta should be 90 degree. Means what? Electric field should make 90 degree to the charged body surface. That is why surface पर जो electric field रहता या just बाहर रहता, वो electric field कैसा रहता? Surface को perpendicular रहता. This is the second point. Third point, net charge inside the interior of the conductor must be zero. कंडक्टर के अंदर नेट चार्ज जीरो होना पड़ेगा. अगर नेट चार्ज जीरो नहीं है मान ले, या चार्ज है मान ले कुछ, या चार्ज है तो you can apply Gauss law around the charge, Gaussian surface you can imagine inside the conductor. Then apply Gauss law, phi is equal to 1 by epsilon 0 into q, Gauss law के हिसाब से. लेकिन phi depends on, phi can be written as integral E bar dot dr bar also, ds bar also. Means what? Electric flux will be present if electric field is there. But in first point we studied, inside the conductor electric field will not be present. If electric field is zero, then charge must be zero. So inside excess charge will not be present. So So that is why if you give charge inside by any somehow, that charge will come on the surface. It cannot remain there because without using Gauss law also you can tell if the charge remains there, it will form electric field inside. But inside electric field cannot exist now, as first point. That is why charge should not be exist. That's why inside interior में charge नहीं रहेगा, surface पर आ जाएगा. Next, fourth point. Electrostatic potential is constant throughout the volume of the conductor and has the same value as on its surface. Surface पर potential कितना रहेगा, अंदर में कहीं भी potential उतना ही रहेगा. ये बात प्रूफ करने के लिए I have taken 2 points. B point interior में, A point surface पर. Now I am going to apply E is equal to minus dV by dr formula. ये फार्मूला अप्लाई करें तो ये अंदर में इलेक्ट्रिक फील्ड नहीं है ना, इस तरह इलेक्ट्रिक फील्ड जीरो ना, ऑलरेडी वी नो इलेक्ट्रिक फील्ड जीरो कंडक्टर के अंदर. सो ई के स्थान में जीरो डाल दिया. मीन्स व्हाट, माइनस डीवी बाई डी आर इज जीरो. दैट मीन्स डीवी इज जीरो. मीन्स व्हाट, पोटेंशियल में डिफरेंस जीरो. मीन्स व्हाट, बी पॉइंट के पोटेंशियल ए पॉइंट पोटेंशियल में डिफरेंस जीरो. मीन्स व्हाट, वी बी इज इक्वल वी ए. मीन्स व्हाट, पोटेंशियल एट बी एंड पोटेंशियल एट ए मस्ट बी इक्वल. That is what, inside at any point potential should be equal to that on the surface. That is why the whole volume we can call as equipotential volume. The whole volume of the charged conductor we can call equipotential volume. Next point, electric field at the surface of the charged conductor. Charged conductor के surface पर electric field कितना है find करना. Find करने के लिए I have taken charged body here, and at this point imagine the charge density is a sigma. I have taken small Gaussian cylinder. Here flat area, here flat area. Now Gauss law if you apply, flux is given by E bar dot ds bar. Here this is a ds bar, small area, its direction is inside to outside. This is ds bar, and ds bar whose direction is inside to outside, and the electric field is always perpendicular to surface, and surface is perpendicular. Means what, it is also along ds bar. So flux must be equal to E bar dot ds bar, that is EDS. But by Gauss law flux is equal to 1 by epsilon 0 to charge present inside the Gaussian surface. Gaussian surface के अंदर में कितना charge है? So 1 by epsilon 0 to charge is a flux according to Gauss law. But according to, by seeing the diagram, flux we found E bar dot ds bar, that is EDS. Inside here, this surface of flux is not there because this is inside the conductor. Inside the conductor field will not be there. So through this flat area there is no flux. Through this outside flat area only flux is there. That flux and E bar is perpendicular to surface. ds bar is inside to outside. In that way E bar and ds bar are in same direction, and between them angle is zero. That's why E bar dot ds bar become EDS. So flux answer is EDS by seeing the diagram. By Gauss law flux is 1 by epsilon 0 to q. So both flux if we equate, EDS is equal to 1 by epsilon 0 q. But q can be written as charge density sigma into ds. So q के sum is sigma into ds. Then ds got cancelled, sigma by epsilon 0 we got. That is why electric field on the surface and just outside is sigma by epsilon 0. And n cap we put because it is perpendicular to surface. Perpendicular to surface, unit vector imagine n cap. So n cap is we should keep, which shows that field is in perpendicular to surface in outward direction. So in that way electric field is in outward direction perpendicular to surface. And the last point is surface charge density will not be same if the charged conductor is irregular shaped. So wherever the charged surface is sharp like this, their surface charge density sigma s will be very high. Wherever the charged body surface is flat like this, their surface charge density is very less. To prove this one point, I have taken two conductors. One small sphere with small r and it has charge q. One bigger sphere has a big q charge, and both are connected with one wire. That means what? They should be at same potential because charge is in equilibrium. Means what? Charge is not flowing. Means what? Charge always flows from high potential to low potential. Charge is not flowing means what? There is a static equilibrium. Means what? Not flowing means what? Both potentials are same. So its potential, how much? 1 by 4 pi epsilon 0 charge by radius. Its potential 1 by 4 pi epsilon 0 charge by radius. But a charge can be written as a surface area into density sigma s. Here also charge can be written as surface area 4 pi r square into sigma f, density charge density by this. So then we got cancellations. Then we got sigma s by sigma f is equal to v is greater than 1. Means what? Sigma s is greater than sigma f. Means what? The charge density at sigma at a sharp point, sharp sphere is always greater than the charge density in the big sphere. So that means what? The spherical surface whose radius is very small, which is called sharp surface, their charge density is always greater. Then flat surface whose radius is very much greater, then charge density is very less.